All right, so we have written down the Green's function for the problem in question. And the next step is, of course, to construct the general solution. The general solution, of course, as we have discussed, is the incoming plane wave, which we write as e to the ik dot r plus integral d cubed r prime So remember that r prime is a dummy variable of integration. So this is an important thing to understand because it is not that I'm integrating over all the angles. The angular information is still there. It is r is basically a function of theta phi and r prime is a theta prime, phi prime, and r prime. Okay. So if you're confused about both these integrations appearing, so please note that r prime, typically this integration is valid only over a small range. Even though we will integrate over entire space, we will assume that r prime goes from 0 to infinity. The modulus r prime goes from 0 to infinity. Usually the potential falls off at large distances. The v of r prime is such that it only has support for some finite range of r prime. So even though we will do this integration over all space, typically the most of the contribution of this integration will come from regions where v of r prime is non-zero. Okay. So for example, if you have a potential that falls off like 1 over r cubed, then you can easily understand that even though I formally integrate from 0 to infinity, at infinity, there's not going to be much of a contribution. So for example, in electrostatics, what you do is you have some kind of a charge distribution here, right? So actually make this very big. You have a charge distribution here and you're asking what is the potential at this point, right? So so let us say that this point P, so let us say that this is your origin of coordinates, right? And then this point P has a vector R. So let us say this is your vector R. Now the potential, the point P is of course a function of R vector, sorry. It's a function of the distance R, right? Now, but I'm only considering charge distribution in this finite volume. Let's call this volume some V. Okay, so the way you actually do these integrations is by taking a small amount of charge in some small region d cubed r prime, right? And then you claim that the charge in this region is dq is basically charge density times d cubed r prime. And then you integrate over r prime, right? So d cubed r prime, and then you say dq over r prime, something like this. Sorry, you basically say this is integral dq over r prime. This is equal to rho d cubed r prime over r prime. So the integration is over the r prime variable because you're integrating over the region where there is a non-zero charge. But the answer to the integration is a function of r, which is the distance of the point P where you want the potential. Okay, so this is kind of similar. So the integration is over the region where the potential is non-zero. But of course, the function that you get is a function of r, and r is the point at which you want the value of the wave function. Okay, so this is your scattering center. Let us say this is the region where v is not equal to 0, and after this region, let us say v just basically boils down to 0. Then I am looking for the wave function at a region which is very, very far from r prime. Typically, that is what I'm doing, even though that information is not contained here, because this is true for any particular r and any particular r prime. This formula that I've written down. Ideally, what I would demand is what is the asymptotic form of the wave function, because that is what we've always worked with. And when you look at the asymptotic form of the wave function, I will be looking at regions R, which is much greater than R prime. Okay, R prime is the region of integration. Okay, so this is a point that I'll be making, and this can lead to some kind of a confusion because it might look like I'm integrating over all the angles, but I'm not integrating over all the angles. We will actually do an explicit example, if time permits today, wherein you will actually see where the angular dependence comes from. So this is the solution to the scattering problem, the way we have set it up. So let us actually plug this in the Green's function that we have forgotten. This is equal to e to the I k dot r minus 1 over 4 pi times integral d cubed r prime e to the I k r minus r prime. Okay. Now, even though I've excuse me, even though I've assumed that the potential is rotationally invariant, everything up till this point will be true even if the potential is not rotationally invariant. In other words, if v is not just a function of the distance r, but it's a function of the vector r prime. Okay, even then this formulation would still be true. Okay, but of course I'll be looking at potentials that are rotationally invariant, but this point is important to me because there is nothing in this formalism thus far that tells you that you have to restrict yourself to rotationally invariant potentials. Okay? So this is applicable for a wide class of potentials, but we will be looking at rotationally invariant potentials where v is only a function of the distance r prime and not the vector r prime. All right. So now let us take the asymptotic limit. So remember that as we just was answering some of the questions, we wrote down a general formula, general asymptotic form. The size scattered we wrote down should be of this form. Okay. So we will try to see if this is actually of that form or not, and how do I make the formal connection. Okay. Now, before I do that, I already see this form emerging. Right? The form of the Green's function is of the form e to the I k r minus r prime divided by r minus r prime. So it sort of looks like a spherical wave, except that I have an r prime floating around. But if I want to take the asymptotic limit, of this equation, so let us calculate the Green's function and the asymptotic limit r much greater than r prime. Okay, where r is of course and r prime is. All right. So let us look at this limit. So the Green's function has this particular guy, right? R minus r prime divided by r minus r prime. Now it is tempting to throw away the r prime completely and just write this as e to the ikr over r and claim that we have a spherical wave. But if we do that, we will lose all information about scattering, as we will see in a few minutes. Okay, the way you should take this asymptotic limit is as follows. So let us look at the modulus r minus r prime. What is this? This is basically square root of r minus r prime vector dot r minus r prime vector. And this is equal to square root of r square plus r prime square minus 2r dot r prime. So if you have any questions at any point, please stop me. Now, since I'm looking at distances r much greater than r prime, within this square root, I have a quadratic form of r prime square, and I have a term that is linear in r prime. So since I am comparing everything to the r square term as the first term, I can throw away the r prime square part in comparison to the linear term in r prime, because r prime is a small quantity in comparison to r. In other words, if I take out r from this equation, I get 1 minus 2r dot r prime over r plus r prime square over r square, right? Which I can write as, since r vector can be written as r times the vector r, so I can write this as r 1 minus 2. The r cancels with the denominator here when I write r vector as r times r cap. So I'll have 2 r cap dot r prime plus r prime square over r square. Okay, and then looking at this form, it certainly seems reasonable that I neglect this guy compared to the linear term. Okay, so which is what I will be doing. So if I neglect this compared to the linear term, I can write this distance r minus r prime approximately as r times square root of 1 minus 2 r cap over r prime vector. And now I apply the binomial theorem. Okay, so this is basically roughly equal to r times 1 minus r cap dot r prime. Okay, using the formula 1 minus x to the n is approximately 1 minus nx plus blah blah. So this is how I will approximate the distances because I'm looking at the asymptotic limit. So now if I apply this in the numerator and denominator, this guy looks like e to the ik, okay, r 1 minus r cap dot r prime let me say an r here. Sorry, just give me 1 second. So I'm pulling out an r square here. So this should be an r square actually, not an r. Forgive me. Okay. So this actually should be over r. And this is also divided by r, and this is divided by r. So basically inside the square root, I'm pulling out a factor of r square. If I pull out a factor of r square, the first term is just 1. The second term is r prime square over r square. And the third term is minus 2 r vector dot r prime vector divided by r square. So instead of r square, I wrote r. So which is why I missed a factor of r everywhere. Okay. So this also has to be over r divided by, again, r times 1 minus r cap r prime over r. Okay. So now if I write this down, remember that the numerator can be simply written as e to the ikr times e to the minus ik r cap dot r prime vector. Okay, so those are the two terms in the, that's the term in the numerator. And the denominator can be written as r times, again I'll apply the binomial formula and write this as 1 plus r cap dot r prime over r plus blah blah blah. But if you look at the second term, r, so this guy, this goes like 1 over r squared. The first term goes like 1 over r, the second term goes like 1 over r squared. So since I'm looking at very large distances, I will neglect the second term and I will write this approximately as e to the ikr over r times e to the minus ik r cap dot r prime. So this is how my Green's function looks like in the asymptotic limit up to a multiplicative constant. Okay. Are these approximations clear to everybody? Is there any questions? There is nothing deep about this. I'm simply taking the limit in which r prime is smaller than r. So if I substitute everything, then my wave function looks like k dot r minus, what did I have? Average per square times 1 more. Times the integral d cubed r prime e to the I, this becomes e to the ikr over r e to the minus ikr cap dot r prime v of r prime psi of r prime. Okay, so this is what it looks like, which I can write, since the integration is over r prime and not r, the e to the ikr over r is just a constant as far as the integration is concerned. So I can write this as e to the ik dot r minus or plus minus 2n over h bar square 1 over 4 pi times the integral the whole thing multiplied by, okay. So now you see a familiar form emerging. So the asymptotic form of the Lippmann-Schwinger equation looks like an incoming plane wave e to the ikr over e to the ik dot r plus some complicated object times e to the ikr over r. E to the ikr over r is your usual outgoing spherical wave. Okay, and this is the incoming plane wave. Of course, this is still not a formal solution of psi of r, because to find psi of r, I need psi of r prime on the left. So I need to understand how to interpret this equation, where at least we are getting closer and closer to the asymptotic form of the wave function. Okay. So the next goal is, of course, to make sense of the square bracket. So how do I make sense of the square bracket? The way you make sense of the square bracket is by turning to what is called the Born series after the physicist Max Born. What is the Born series? Well, basically, the Born series is not very difficult to understand. It is true that formally this is not really a solution, because I need to figure out psi of r to find psi of r, but I can still understand this psi of this equation as follows. Suppose if my potential is weak, okay, then I can always write my psi of r as some kind of a series. Just like you do in ordinary perturbation theory. So what is the leading order term of this series? The leading order term of this series is phi 0 r plus n equals 1 to infinity of phi n r, where phi 0 r is basically what I would have if there was no scattering. If there was no scattering, if there was no potential, then there is nothing to obstruct the incoming plane wave. So phi 0 to 0th order, when there is no scattering, should just be the incoming plane wave, right? There can be nothing else. And all non-trivial aspects of scattering is contained in the second series phi n of r vector. Okay. So as long as the potential is weak, one can always argue that such a series will converge. So we'll not worry about the exact mathematical aspects of convergence of this series. We'll simply assume that this series converges as long as the potential is weak. So with your knowledge of perturbation theory, you can actually try to understand this as follows. The n equals 1 term should have one factor of potential. The n equals 2 term should have two factors of potential, and so on and so forth. We'll explicitly show this maybe tomorrow. So if the potential is weak, you can always argue that the higher order terms will be progressively weaker. Okay. So suppose if I want the solution to, let us say, the first order, then on the left hand side, I want the solution to first order. Then I can feed the solution to n equal to 0, 0th order on the right hand side, because the right hand side already has a potential v of r prime. There is no point introducing another to first order on the right hand side, because that will be second order. Okay, since the first order term phi 1 of r vector is already a function of the potential by assumption, there is no need to feed in the first order term on the right hand side if our goal is to figure out the first order correction. So if I want everything to first order, then psi of r will be e to the ik dot r plus the square bracket times e to the ikr over r, where the square bracket will be evaluated assuming psi of r prime on the left is n equal to 0. The advantage of this formalism is that you know exactly what n equal to 0 is. N equal to 0 is just the plane wave. So the first order approximation, and usually people call this the Born approximation. But remember that Born approximation is true for whatever order you're working with. Okay, so if I want the n plus 1th order, then on the right hand side, I should put in the solution to nth order. So I will evaluate things order by order, but usually we'll just stick to first order because more than that is one, quite complicated, and two, in most practical cases, rather unnecessary. So what is the first order approximation? First order Born approximation. The first order Born approximation is psi of r is e to the ik dot r plus minus 2m over h bar square 1 over 4 pi d cubed r prime e to the minus ik r cap over r prime b r prime. And here I'll have to put in the solution to psi of r vector prime is the solution to n equal to 0. So remember always, if you want the solution to nth order, on the right hand side, feed in the n minus 1th order. So if I want the first order, on the right hand side, I'll feed in the 0th order. The 0th order is something I actually know. This is e to the ik dot r prime, sorry, because I'm looking at psi of r prime. The whole thing multiplied, of course, by the spherical wave e to the ikr over r. So now let us clean up the notation, and now you will actually see the connection between this and the asymptotic form of the wave function that we wrote down earlier. Inside this integration, I have minus ik r cap dot r vector prime times e to the ik dot r prime. Okay. Now, e to the ik dot r prime, the k there is of course the initial momentum. So if I want, I can write this as e to the iki dot r prime. Okay. Now, what is the final momentum? The final momentum is also k, because by energy conservation, if I'm looking at asymptotic regions where there is no potential, it's only kinetic energy. So if the kinetic energy has to balance, which means the momentum has to balance. So the final momentum should also be the same as the initial momentum. So it is no surprise that the e to the minus ik r cap, the value of k, their modulus of k, is the same as the initial momentum k. But the direction is slightly different, right? So this direction is along the r cap direction because it is the outgoing spherical wave. So you can say that kf is kr. Even though the magnitude is the same, the direction is that of an outgoing spherical wave in the r cap region. So this whole exponential can now be written as e to the I ki minus kf dot r prime vector. Okay, ki minus kf is the momentum transferred from the incoming to the outgoing wave. Okay, so I will use a slightly different notation. Ki minus kf, I will call some q. Q is the momentum transfer. This is the standard notation that you will find in every textbook. Okay, so what I mean is this. So suppose if my initial momentum is along some direction, let us say this direction. Okay, my final momentum is along this direction. Okay, so this is my ki, this is my kf. Okay, now this distance would be my q vector. Excuse me. So an initial wave that has a momentum ki vector is scattered into a final wave with momentum kf vector, and the angle between the initial and the final momenta is of course the scattering angle, the angle by which the initial wave is scattered. Okay, so all information about the scattering angle is contained in q vector. So this is the point that I wanted to make. Okay, now remember that if I do this integration over r prime is a dummy variable that has nothing to do with the scattering angle, I will get a function of q. And if I get a function of q, that means that my scattering angle information is hidden inside q. So it is not like when I do the integration over r prime, I lose all information about the angle. All information about the angle is contained in my q. We will demonstrate this explicitly in a short while. So putting everything together, my psi of r in first order Born approximation can be written as e to the ik dot r minus, I'll write this as minus m over 2 pi h bar square, right? So this is 2m over h bar square times 1 over 4 pi integral d cubed r prime v r prime times all that remains is e to the I q dot r prime, the whole thing multiplied by e to the ikr over r. So now you can make a formal connection. Since our asymptotic form of the scattered wave should be of the form ansatz is that psi of r is the incoming plane wave. Of course, you can always choose the incoming plane wave to be along the z direction. So I can write this as e to the ikz, but I'll now leave it as e to the ik dot r plus f of theta comma phi e to the ikr over r, right? So if you compare these two equations, then from the Lippmann-Schwinger equation, there is a very easy way to determine the scattering amplitude f of theta comma phi, and this is nothing but integral d cubed r prime v of r prime e to the I q dot r prime. Okay. But if you stare at this, you know exactly what this is. Integral d cubed r prime v of r prime e to the I q dot r prime is exactly the definition of the Fourier transform of the potential, right? The Fourier transform of any function of r is integral d cubed r f of r e to the I q dot r. So this is basically the Fourier transform of the potential v of r. Okay. So I'll call this v tilde q. This is our usual notation. So f of theta comma phi can be written as minus m over 2 pi h bar square v tilde q. Okay. Now, one important point here, and I'll also put this as part of the tutorial. Remember, in a lecture or two ago, when we derived the Green's function, I made the point that I have to choose the minus I epsilon prescription here. So for example, here, when I wrote down the Green's function, I wrote down minus I epsilon and not plus I epsilon. I told you that this fact is important in this particular problem. So the reason this is important in this problem is that if I had chosen aside note that if we had chosen the plus I epsilon prescription to compute the Green's function. I don't seem to be able to write green. green function, we would have derived psi of r equals e to the I k dot r plus f of theta comma phi. This part would have been similar, but here we would have had a minus ikr over r. Okay. Now I want you guys to check this by explicitly calculating the Green's function and showing that for the other prescription A plus I epsilon, your Green's function would have looked like e to the minus ik r minus r prime divided by r minus r prime. Okay. Now this is unphysical because the second term here represents an incoming spherical wave and not an outgoing spherical wave. Okay, since this is an incoming spherical wave, this cannot be a valid solution in the scattered region because we are looking explicitly at a wave, at a particle that is being scattered by a potential and moves outward and moves away from the potential. It's a repulsive potential, so it is moving away from the potential. So it is not moving into the potential, which means we cannot have an incoming spherical wave in the scattered region. Okay. So this is why the I epsilon prescription in this particular problem is crucial. We cannot choose the wrong I epsilon prescription. Now, if we did, then we would have gotten an unphysical result for the scattered wave. So now that we have the scattering amplitude, we can go ahead and get them in the differential cross section. So sometimes this is, of course, scattering amplitude to first order in the bond series, right? So some people also write F1 or F0 or something like that, but I will not employ that notation. But please understand that the fact that the scattering amplitude is simply the Fourier transform of the potential is a result that is only valid to lowest order in the bond series. So d sigma over d omega is of course the absolute modulus square of f, and this is equal to m over 2 pi h bar square quantity square times the Fourier transform of the potential quantity square. Okay, so these are the two major results in the lowest order bond series, and the only non-trivial part is of course simply calculating the Fourier transform of the potential. Once you know the Fourier transform of the potential to lowest order in the bond series, then you're golden. Okay, so we will develop a way to calculate this. So we'll just write down this integral in a slightly more elaborate form and then stop for today. And tomorrow or in the tutorial, we will do a particular exam. Okay. Are there any questions up till now? Any questions or comments? Okay. So since I'm looking at a rotationally invariant potential, I can always choose my Q to be along the polar axis of the integration variable. So if I'm looking at this integral d cubed r prime e to the I q dot r prime, where q is some vector as far as this integration is concerned, v of r prime. Now notice that there is no phi variable here because v is independent of phi and q dot r prime is also independent of phi. So the phi integration can be trivially done, and that gives you just a factor of 2 pi. And what I have is r prime going to 0 to infinity, r prime square dr prime minus 1 to 1 d cosine theta e to the I q r prime cosine theta prime. Okay, and then there is also a v of r prime. So this is the integration that I'm looking at. So remember that this is our usual trick of converting the angular integrals into a form that is easy to do, where I simply write down cosine theta as some x. Okay, so then this integration can be trivially done. So this is 2 pi integral 0 to infinity r prime square v of r prime dr prime, and e to the I q x dx is simply e to the I q r prime cosine theta prime divided by I q r prime between the limits plus 1 and minus 1. Plus 1 and minus 1 for cosine theta, not theta. right? So this is equal to 2 pi. One factor of r prime cancels with one factor of r prime in integration. So this becomes r prime v of r prime. This is basically e to the I q r prime. Actually, let me keep the factor of r prime. Minus e to the minus I q r prime divided by I q r. Okay. Any questions about this? So this, in this form, we can simply substitute, for example, e to the ix minus e to the minus ix over ix is just sine of this angle divided by 2. And then you can use this form to calculate the Fourier transform of the potential.
Sir,
Yes.
do we have theta or theta prime in the integration?
So remember that the integration is over d cubed r prime, which is over r prime, theta prime, and phi prime. So sorry, so I should actually say theta prime, right? Thank you.
Okay.
Okay, so this is not the scattering angle, basically. The scattering angle is hidden in the definition of Q. Any other questions, comments? Okay. So if there is no particular questions at this point, then I would like to stop at this stage, and then we will take this up tomorrow, where we will actually solve a potential. We will solve for the Yukawa potential, and then we'll also take the limit of the Yukawa potential to retrieve the Coulomb scattering, and I will also discuss the limitations of this procedure, and then we'll fully finish off this example in the next lecture. So that will prepare you for solving the tutorial problems in the scattering series. So at this point, I will stop for today, and then we will continue tomorrow. We will take this up at this point and then basically solve an example in class tomorrow.